Okay, this question asks, study is conducted to compare the test scores of two groups of students who have had different test-taking training programs. Group A consists of 30 students who received program X and Group B received program Y. To assess if the normality assumption is met, we would analyze the histogram of the difference in test scores. So if you want to check the normality, we have to check the distribution, the sampling distribution of mean is normal. So we have to check about the sample means, not the differences. So this would be false. And the question it specifically asked to fill in the circles. So I will fill in the circles. So false. Okay, this question asks, in a match pair design, a study is conducted to assess the effectiveness of a new test-taking training program. A group of 30 students is selected, and their test-taking performances is measured before and after. To assess if the normality assumption is met, we would analyze separately the histograms of the scores before the training intervention and the scores after the training intervention. So this question, the statement is false because in a match pair design, it would be better to do to analyze the histograms of the scores at the same time. So it's more appropriate to analyze the distribution of the differences between the paired observations rather than analyzing separately. So this would be false. I will fill in, just like the question asked. So that's that. And let's try for the next question. So data is to be generated from a population to test the statistical hypothesis. Sigma is 85 and the significance level is 0.01. And then mu naught is 150, and then CA is 2.328648, something like that. So the power for detecting the alternative of mu A, so the power equation is just like how you solve for the Z distribution, which is just like this: mu naught minus mu A over mu sigma divided by square root of m. So if you do that, that becomes 150 minus 180 over 85 square root of 100. That just becomes 30 over 85 divided by 10. So that becomes negative 30, sorry. So negative 30 over 85 over 10. So that becomes around negative 1.20. If you do the calculation, negative 1.2031 if you do the calculation. So this is indeed right, where Z is a standard normal variation. So this is true for question 3. Okay, so let's move on to the next question of 1.4. Okay, 1.4, a farmer wants to determine the most effective fertilizer for 3 different kinds of crops: corn, wheat, and soybeans. The farm has a large field where these crops are cultivated, and so the farmer suspects that the field's soil quality and drainage can vary across different sections of the field. To account for this variability, the farmer decides to section off the field and conduct a randomized block design. Okay, and the question asks, in this scenario, the blocks of the randomized block design would be the different types of fertilizer. That would be false because the variability would be the soil quality and the drainage. So it would be better to put soil quality and drainage as the block design blocks, not the different types. So that's why it's false. So the blocks would be soil quality and drainage. Okay, 1.5. In situations where it is known or suspected that individual differences can affect the response and potentially mask the treatment effects, then a completely randomized design is the most appropriate experimental design technique. So for this question, evaluate whether the completely randomized design would be the most appropriate one. Since we are known that the suspected that when it is known or suspected that individual differences can affect the response and potentially mask the treatment effect, a completely randomized design might not be the most appropriate experimental design. So, in this case, completely randomized designs can allocate treatments to subjects randomly without considering individual differences, which can lead to confounding and reduce statistical power. So, the techniques like the controlled experiment would be a better choice compared to the completely randomized design. So by this reason, this statement is false. And 1.6, the sample size, 95% confidence interval, sigma is equal to 215.044, and the confidence interval is that, the critical value is that, and we're interested in finding the sample size, basically. So if you remember your margin of error is critical value times standard deviation divided by square root of n, right? And this value is equal to the half of the width of the confidence interval value, right? So 23.1 plus 52.3, which that becomes minus 52.3, which is why it becomes plus 52.3. So if you calculate that, what do you get? 23.1 plus 52.3, that is 75.4 divided by 2, 37.7. And critical value is given as 1.959964 standard deviation. So that's 215.044, and we're interested in square root of n. Okay. So if you do that, so 37.7 square root of n is equal to 1.959964 times 215.044. So 215.044 times 1.959964, and then divided by 37.7, and then if you do that, you get square root of n value is approximately 11.18. If you square the value, this will be 11.18. Let's do that. 124 point, sorry. So 124.9924. That's square root of n. I mean, it is square root of n. And then if you square it, that just becomes n, not squared n. So that's just n is about 124.9924, which is greater than 100. So it is indeed true. So this is true. Okay, this question asks, when conducting a hypothesis test, the investigator obtained a p-value of 0.002, and that it has a small sample size, and the significance level is 0.05. So, and then it's asking to evaluate A, B, C, D, E. Let's look at A. If the sample consists of only likely events for the population, then it would suggest that either the null hypothesis or one of the model assumptions was incorrect. So this is true because a low p-value, meaning that the observed data is unlikely under the null hypothesis, so rejecting the null hypothesis. So if the sample consists of only with the likely event from the population, then obtaining a low p-value would cast doubt on, I guess, whether the null hypothesis is right or one of the assumptions is right. So A is right. And then if all assumptions were correct and H naught is true, the data was an unlikely event. So if all model assumptions were met, and then H naught is true, then it is going to be unlikely event, because the low p-value suggests that the observed data is unlikely to occur. So null hypothesis is rejected, which is why it's going to be unlikely event. So A and B is right. So that makes the C not right, because it's basically the opposite of B. So D, the null hypothesis H naught is false. You cannot say that null hypothesis H naught is false. You can say that we are rejecting the null hypothesis, like we have evidence to reject the null hypothesis, but that doesn't mean that it is false. So that means option A and B is right. So that's going to make option E the right answer. Okay, let's look at the next question. In a preliminary study, a 99% of a confidence interval for an unknown population mean was computed using a sample of 32 observations. Okay, standard deviation was 16, and the confidence interval is that. So they want the width of the confidence interval to be no more than 6 units long, using the 99% critical value of 2.5758, and determine the minimal sample size. Okay, required to achieve 99% confidence interval of no more than 6 units in width. For this question, you can use the marginal error. So marginal error is the half of the confidence interval. So half of the width of the confidence interval, and width is 6 units long, so it's gonna be half. One half times 6, that would be the margin of error. And margin of error can also be found by using the same equation that we used in the above. So like the critical value, which is 2.5758 times the standard deviation value. So standard deviation value is 16. And then you divide that value by the square root of the sample size, which is n, which is the one that we are interested in looking for, right? So this value becomes just 3, right? 3 is equal to 2.5758 times 16. So 3 square root of m is 2.5758 times 16. Square root of m is 2.5758 times 16 over 3. And that n would be n value is just 2.5758 times 16 over 3 squared. So if you do that, let's plug it in. 2.5758 times 16 divided by 3 and then square it. If you do that, you will get something like 188.7217-ish value. But the sample size must be an integer. We don't have 188.7217 sample size, right? So it has to be a whole number. So if you round it up, that becomes 189. So the sample size would be 189. Okay. Next question, 2.3. So an SRS is taken from the population to test statistics for one-sided upper tail test has p-value of 0.04. Now, if you're going to conduct a two-tail test, what conclusion could you make at the significance level of 0.05? So if it's two-tail test, you multiply the p-value by 2 from the one-sided p-value, which is 0.04. So 2 times 0.04 is 0.08. So two-tail test p-value is 0.08. And then you compare that value with the significance level, which is making greater, because 0.08 is greater than 0.05. So that means you cannot reject the null hypothesis. So this is not D, and then this is two-sided, right? So it's not less than. If it's two-tailed, then it's going to be either equal or not equal. So it's going to be, we do not have evidence that the 5% significance level that the population mean differs from the null value. Because we cannot reject null. So that makes B the right answer. This question asks, to investigate, researchers conducted a 6-month experiment with randomly assigned volunteers to a placebo or supplement. Discomfort and pain levels are assessed, and D value is the average difference in discomfort and pain values for the supplement group, which is greater than 0. So that is the alternative. So HA is D value is greater than 0, right? So then H0 is D is less than 0. Okay, that is important to note because the type 1 error is basically false positive. So even though we rejected the null hypothesis, that is actually true in the population. So let's look at the options now. Option A, type 1 error means concluding that dietary supplement does not increase discomfort or pain when there is no actual increase in discomfort. So, dietary supplement does increase discomfort. So it's false positive. So it rejected the null hypothesis, right? Because alternative is the increasing. But in reality, the null hypothesis is true, that means there wasn't an actual increase. So that is right by definition. But the negative consequences can be led by a viable product or the loss of potential profit. That is right. Okay, so A seems like A is the right answer. Let's just go through the B, C, D, E. So B, concluding that it has a significant effect on reducing discomfort when it does not. So type 1 error, the dietary supplement has a significant effect. We can't, let's see. Since we're not given any p-value, we don't know it has a significant effect, but also would mean concluding that significant reducing, type 1 error is a false positive. That means it rejected the null hypothesis. That means it increased the discomfort. So that is definitely the opposite. So it's not. It has to be reject the null hypothesis. So you cannot say it has a reducing discomfort because it already rejected the null hypothesis. But in reality, it is not. So this is just not the right answer. So C, and then significant on improving the cholesterol level. Are we interested in cholesterol level? I thought it was discomfort and pain level. So, okay, so cholesterol level does not have anything to do with this problem. So C is not right. And D, type 1 error would mean concluding that the dietary supplement does not have a significant effect on improving cholesterol level. Yeah, cholesterol level does not have anything to do with this question because we're interested in the pain, discomfort and pain level, not cholesterol. So the cholesterols are gone. E, a type 1 error would mean concluding that the dietary supplement does not have a significant effect on reducing when it does. So this is type 1 error is false positive, so rejecting the null hypothesis. So null is not true, but in reality it is true. So it's basically saying does not have significant effect on reducing the discomfort. So it did does not have a significant effect. No, it's not rejecting the null hypothesis. If you're rejecting the null hypothesis, it should have said it's increasing the discomfort, not reducing. So it's not E. So the answer is indeed A. So next question, 2.5. In the following experimental design diagram, what is missing? So in the experiment, you have to have randomization, right? And if you look at block 1, 2, 3, it has treatment group and recording, but there's no randomization. There's no specific way how it is randomized to put the participants into block 1 or 2 or 3. So the correct option is indeed B. Okay, this question, a major source of profit for a new video streaming company, YouTube, okay, not YouTube apparently, is the advertisements that are played before their videos begin. The company charges their ad clients a rate per second watch. Therefore, it is of importance for YouTube to find out how long the users are willing to wait before they skip ad. So the first 400 newly registered users were chosen, and then the company randomly assigned 4, 5, 6, or 7 seconds to wait for the skip ad option. And thus, each group has 100 participants. After 1 month, they will record the activity, ranging from 1 and 10, which reflects how active the user is on the platform at the moment of recording. So what are the units, treatment factors, including the levels, and response variable? Okay, so the units, we said there's 400 newly registered users, so there's 400 users. I guess, newly registered, yeah. It's good to be specific. 400 newly registered users, and then the treatment factors. So treatment factors would be the time before the skip ad option. That will determine on how the experiment works. And also the levels since we said we're going to randomly assign 4, 5, 6, 7, that would be our levels. 4, 5, 6, 7, 4, 5, 6, 7. There we go. And the response variable. And response variable, after 1 month, they record the activity score. So the activity score of each user ranging between 1 to 10. Okay, so that's A. So part B is asking whether it's observation study or experiment. So if it's observational study, then it's been like just observing without controlling anything. But then this question is actually experiment because we're having a specific requirement. The company is assigning the number of seconds. So company is actually being involved in this, like, I guess, study or experiment. More like I should just say that case. Let's say that. So the company is actually being involved in this case by having skipping ads option appears. So they're assigning the number of seconds until the skip ad options appears. That is controlling this experiment, which is why it is experiment. So the reason you can say that the company is assigning, my handwriting is not the best, the number of seconds until the skip ad option appears. And part C, state 1 lurking variable. So the lurking variable is, by definition, it is a variable that is not included in the analysis, but it can still affect the outcome of the analysis. So the lurking variables can be, let's say, the people's preference on what type of shows, what types of videos, and so like basically what types of videos they're watching, what types of videos, and why they're watching, and the options of platforms that the user can use. Right. And then part D is asking, you're asked to consult on the design for a new version of this study. Describe 1 specific change that can be made to ensure that the new study provides a more convincing result. Okay, so you can use any of this lurking variable to do that. So you can have something like, you can restrict a user to only certain types of videos. To only certain types of, not certain types of videos, but like you can restrict a user to a certain types. The certain types of videos, right? You can restrict users to only watch certain types of videos, or you can do something like why they're watching videos. So you can restrict. It will be difficult to do the why part, but I think the videos they're watching, you can control those. So I think you can do something with controlling what videos they're watching. And this will help with the principle of control that all of the users are viewing the certain video types. You can do the reason. If I just think again, I guess you can do the reason. So if you do the reasoning, this will also help the principle of control that all of the users are viewing the videos for the same reason. So you can do that. So any of the mentioned above for the lurking variables, you can use that to elaborate on part D. So I think the main point of this question is basically you know how to use your C to make a better experiment and use the principle of control to elaborate your justification. Okay, this question is asking, a box of cereal produced by company A is labeled to contain 20 ounces of cereal. And to understand the situation better, the company took a random sample of 50 boxes. Okay, and our output which is I just copied in here. It's tiny. I'll just zoom in for later. But then it's asking the data provides. Does the data provide any evidence that the true mean weight is not 20? And perform the four-step hypothesis test with alpha value is 0.08. And be sure to use at least 4 non-zero digits in the p-values. Okay, cool. So when you're doing the four-step hypothesis, the first step is to define the parameters, right? So let's do that. Let's do mu of x as the pop mean weight of the cereal box. Or you can do the true mean. Yeah, you can just do that. The true mean weight of the cereal boxes. Okay, and then you have to state your hypothesis. So since we're curious in whether knowing A is not equals to 20, so our alternative would be mu is not equal to 20. So mu naught would be mu is equal to 20. Okay, and then using that we have to get the test statistics, DF, and p-value, right? So let's look at our output now. So 1, 2, 3, 4, 5, 6. So since this is not less or greater, right? So that means not output 2 or 3. And 5 and 6 is also not right. So it's going to be either 1 or 4. That's good to know. Okay, and then our mu value is actually 20, right? So this is two-sided mu, right? So that's gonna make the output 4 the right choice. Okay, so now we just have to state the test statistics value was negative 2.7893. And the F value is just m minus 1, which is 50 minus 1, which is 49. And p-value, which we just have to copy from the output, which is 0.007501. So 0.007501. That's your p-value. Okay, we have that. And now we just have to conclude. So conclusion is since our 0.007501 value is less than our significance level, what is it? I know it was less, 0.08. This is way less. So we are going to reject the null hypothesis. So we can say reject null or reject H naught because 0.007501 is less than 0.08. And then we can say that the data does not support that to the claim that the true mean weight, the data does not support the true mean is 20. Because 0.007501 is less than 0.08. So we are saying that the data does not support the claim that the true mean is 20. We're rejecting the null hypothesis and we're giving the reasoning. So that is it for the part A. And then should you use confidence interval, lower confidence bound, or upper confidence bound? So if you remember your alternative, you use two-tailed, right? No, two-tailed, and alternative you use not equal sign, and this was the two-tailed, right? If it's not equal sign, you have to use confidence interval. So confidence interval is 1 minus alpha, right? So that means 1 minus 0.08, that just becomes 0.92. So 0.92 is the correct confidence level. So part C, let's look at that. If you stated an interval in part B, would you predict the null value would be inside or outside? If you stated a bound in part B, would you predict the null value would be greater or less? Okay, so we selected interval in part B, and then we said the null value was 20, and we rejected the null hypothesis, right? So it should be outside. This is because we rejected the null hypothesis. So this 20 value is outside. And then write down the correct critical value for the confidence interval or bound in part B. Okay, so now let's go back to your output. Let me just copy paste this output 7. Hold on, there we go. Let's copy and put it in here, if I can do that. Yeah, should be good enough. I can still see it. Yeah, I will just zoom in. So let's see. So this one is two-tailed, right? So if it's two-tailed, it shouldn't be just like this. You should have something divided by 2. So it's gonna be either this one or that one. This one, this one, this one, this one. So the rest is not right. But then you should also include the DF value, right? So that makes this not the right option. So it's gonna be this one or that one. And then if you look at the lower dot tail equals true and lower dot tail is equal to false. So since we're interested in the value that, I guess, the left side of the normal curve, right? So that would make that this one 1.787758. So critical value would be 787758. There we go. That's the correct output. Yeah. Okay, this question E asks a statistician associated with a company A argued that instead of using the sample standard deviation, they should use the population standard deviation known to be 0.1. Okay, so if you use the population standard deviation, this will change into C distribution, since this C distribution deals with the population standard deviation. So that will change the critical value, yes. So if you're changing the critical value, let's look at the options. So again, in output 7, I'll erase all. So it's no longer be this 2, no longer be this, yeah. And then since it is still two-tailed, that means the p-value should be not the p-value, the significance level should still be divided by 2. That means those are not right. Those are also not right. But then in the C distribution, you don't have to include your degrees of freedom. That's why you get rid of those. So it's going to be either this or that. But then we're interested in the lower tail equals false because we're interested in the left side of the normal curve. So the right option would be 1.750686, the new critical value. Yeah. So in the practical significance question. So what practical answer would you give to the company about whether the weight of the boxes have changed from 20 ounces? Box weight more than 0.001 ounce different from the stated weight will cause a problem for the company. The appropriate value from the confidence interval is 19.99. The sample mean is 19.96. And the sample standard deviation is 0.0901 ounces. Sorry about that. And yeah, so let's evaluate it. So if you want to evaluate the practical significance, you have to evaluate the effect size and the differences. Let's do the difference first. Difference is 20. So the mu naught value minus 19.99, which is the confidence interval, that is 0.01. And the effect size is the difference over standard deviation. So the difference over ST, difference is 0.01, and ST standard deviation is, okay, we're given 0.0901. If you do this, it's going to be around 0.11. Cool. So if you look at that, the difference is large because our standard is 0.001, right? So 0.01 is much larger than 0.001. So the difference is large, but the effect size is small. So in this case, it is not practically significant. Because if the difference is large, both values have different effect, meaning they're practically different. So this is not particularly important in conclusion. So it's not particularly significant for this part. And then question G. Okay, company B produces a box of cereal weighing 20 ounces. If someone wants to determine if the mean weight of cereal boxes produced by company A and B are different, what type of inference would you need to perform? Choices are 1 sample, 2 sample independent, 2 sample match, or none of the above. So for this one, company B would use 2 sample independent, right? Because they still have to evaluate whether the mean value is different or not. So it's going to be equal or not equal sign. That means it's going to be 2 sample. And then it's also independent because A and B are not correlated. So it's going to be 2 sample independent. And the reasoning is A and B are independent cases and no attribute to match. It's sample units on. Yeah, that is it for question 4. This question asks, a research team is conducting a study to evaluate the effectiveness of a general algorithm modification for generative AI model. Okay, and the R output of various tests is provided on the last page, which I copy pasted in the next page. But note more information is provided than is needed to answer the questions. Okay, so should you use a 2 sample independent or 2 sample match pairs procedure to analyze the data? Okay, I might actually have to read the question again then. The team will use the same fixed set of text prompts to generate images both with and without the new algorithmic modification. And the random sample of different AI models are selected for testing. The Frechet inception distance is a metric that will be used as measurement for the difference between the generated images and the real images. Okay, so now we read all the questions. So what do you think? Independent or the match? I would go with the paired or match pair. So since each pair is matched with the fact that they have the AI model or the same prompt, just like the one that's like highlighted above, so they are correlated. They're not independent of each other. They're like, if it's independent, there will be no sample that can be matched to each other, like the M or S. So this is paired, and the reasoning is each pair is matched with the same AI model or the same text prompts. Yeah, and that's set in the same fixed set of text prompts to generate AI images. That's why. Right. So yeah. So that's not the right highlighted one. This is this part. Same fixed set of text prompts and the same AI model. Right. That's why. And then, if you were to generate a graph, determine whether the assumptions are valid or not, which variables would you be graphing? So if you want to check whether the assumptions are met, you can use the differences between the populations, which we are given in the last thing. So the difference, last, row. The difference between the populations is n minus s. We can use that to check the assumptions. So, is the average FID score lower than when the algorithm modification is implemented to generate the image at a 2.5% level of significance? Okay, so if I do like the m minus s, the difference is the d, capital D equals m minus s. And then if you say h naught is mu of the since we're interested in the H naught, the difference, what are we interested in actually? Okay, let's see. Okay. Oh, lower, I see. Okay, cool. So HD would be greater or equal because we're interested in whether the main difference is lower. So HA, the alternative of mu D less than 0. So that's all of your null and alternative hypothesis. So for question D, for the hypothesis test in C, should you use the confidence interval lower bound or upper bound? Our alternative hypothesis include the less than sign, so we have to use the upper confidence interval. And you'd use the upper confidence bound, sorry. Yeah. So if you want to use the confidence interval, that should be then not equal sign to that. So that's not the case because our alternative has less than sign. So we're going to use upper confidence bound. And part E as interpret the appropriate 97.5% confidence interval or bound, which is bound for us. Please include at least 3 decimal places for the appropriate numbers using this output. Okay. So let's do that. So let's use the output. So we said it is paired. So it's not output 1, 2, 3. It's going to be 4, 5, 6. Okay, and we are also going to use the upper confidence interval, right? So that means upper confidence interval should be negative infinity to some kind of value. So that is output 5. Okay, so we have everything. Now we can write down our interpretation. So we can say we are confident, I guess 97.5% confident. Let me just erase it and just write it in order. 97.5% confident that the difference between the population, I'm just going to use the true mean, between the true mean, it's not weight, sorry, true mean between the algorithmic modification and standard algorithm n minus s is less than, what is it? Oh, 0, yes. Oh no, it's not less than 0. Less than the upper bound. Less than the upper bound of 0.2712962. That value. That's the important value. And at least 3 decimals, so technically you don't have to write all, but if you're rounding it, yeah, make sure to round it in the right place. But I'll just use the output exactly, because why not? Because we're given the output and you can just write it down. So that's that for part E. So let's look at part F now. So based on your answer for part E, what would be the decision for the appropriate hypothesis test for the hypothesis stated in part C? And if you recall, our significance level is 2.5%. So confidence level is 97.5%, but our significance level is 2.5. So if you add 2.5, that becomes 100%. And if you look at our upper level, it's negative infinity to 0.2712962, right? And the 0 value is indeed included in this interval. So it'll be hard to reject. So we can say we would fail to reject because the 0 is included and the confidence level is 100% in this case. So that is it for part 5. Okay, this question, part 6. In computer assignment, part 5b, you explore the relationship of type 1 and type 2 error, power 1 minus b, and sample size n, the standard deviation, blah, blah, blah. Okay, suppose we want to test the following. H naught is mu greater or equal to 76, and HA is mu less than 76. Okay, Now, select the correct code and output for determining the C critical value. So, since our hypothesis is greater than equal and not and less than, not a not equal sign, so that would make B not the right option. If you're dividing by 2, the alternative hypothesis has to have a not equal sign. But since our thing is, I guess, less than, right? So that means lower tail is false, so which is looking at the left side. So that is indeed right for the A. So determine a formula for X cutoff with respect to the null value mu naught. Okay, P type 1 value, type 1 error is, what is it? 0.02. There we go. So P of X bar sample mean X and then X cutoff, given that mu is mu naught, it is 0.02. And then P of C is less than or negative 2.05374 because it's lower tail, and this is this is lower tail value, which is why there's a negative sign, which is the left side. So that is equal to 0.02. And then if you do that, you can write the cutoff formula as X cutoff minus the mu naught over the sigma divided by the square root of n. So you can write this as X cutoff minus mu naught. Mu naught value is, what is it? 76, right? Yeah, 76. And then sigma value is where you're at 16. And then divided by square root of n. That value is equal to this negative 2.05374. Because when you do the standard deviation, you do mu minus mu naught over sigma over square root of n to standardize it. It's basically that without using the mu value, we're going to change it with the X bar cutoff. So this is simple mean of cutoff value, which we are interested in. So you can write this X cutoff value is negative 2.05374 times 16 over square root of n, and then plus 76, because if you move the 76 to the other side, that becomes positive. And then you have to multiply it. Sorry about that. And then part C, write an expression for the probability of type 2 error using X cutoff. So probability of type 2 error is, are we given? Yes, we are given 0.02. That's lovely. Okay. And then type 2 error is P of X bar is greater than the X cutoff. So mu is mu, and given that mu is equal to mu A, sorry. So that becomes 0.02. So we have that for part C. And then standardize the X cutoff. It's the similar logic. So you can do P of C is greater than, and since this is greater than, we can use that 2.05374 as a positive value. Right? That is equal to 0.02. And if you standardize it, this becomes P of C greater than X cutoff minus mu A over sigma over square root of n. This is equal to 0.02. So if you write this, X of cutoff minus mu A over sigma square root of n is equal to this value, 2.05374. Right. And then you can plug it in and find the values. So X cutoff minus mu A value, are we given? We are 60 over square root of sigma is 16, right? Yeah, 16 divided by square root of n. Okay, square root of n. So that value is equal to 2.05374. Yeah, I have no space. let me just move this to here. So is equal to 2.05374. Oh, there we go. So this is our interest value, or the equation, I guess. And then solve your equation for the sample size. Okay, now it's the algebra. And obtain the minimum sample size required to ensure that the type 1 error and the type 2 error has the exact probability alpha is equal to beta for the given alternative of mu a is equal to mu a is equal to 60. Okay, so our x cutoff from the type 1 was negative 2.05374 times 16 over square root of n plus 76, right? And right. I see. Okay. I see. Okay. So technically, we don't even need to use that. I can just see. I'm just gonna copy paste this part and make you visually see it, and then this part. There we go. So do you notice that these values are almost similar except for the negative sign here? So you can do, if you want to set that values are equal to each other, you can do 16 over square root of n, and then what we could do is we can do the multiply by negative sign in both sides for this equation. So let me just erase it and just write it again. Negative square root of negative x bar cutoff plus 76 over 16 square root of n is equal to 2.05374, right? That is equal to x bar cutoff minus 60 over 16 square root of n. So that would mean that let's do that. 16 over square root of n. Right, hold on. Okay, so alpha is equal to beta. Okay, alpha is equal to beta for the given alternative of mu a. Okay, cool. So we're given that x cutoff is negative 2.05374 times 16 over square root of n plus 76, right? Then if we just subtract that by 60 and then divide it by the 16 square root of I see. Yeah, I was just going in a wrong rabbit hole. Okay, cool. Right. I was just thinking something different somehow. Anyways, so since in the parts B, we have the x cutoff is equal to negative 2.05374 times 16 over square root of n plus 76, right? So negative 2.05374 times 16 over square root of n plus 76 minus, you're going to use this equation. So minus 60, we're just exchanging the x cutoff value with the part B value, this one. So if you do that, minus 60 over 16 square root of n is equal to 2.05374. Oh boy. Okay, cool. So that becomes negative 2.05734 times 16 over square root of n plus 16 over 16 square root of n is equal to 2.05374. Lovely. I like that. Negative 2.05374 times 16 over square root of n plus 16 is equal to 2.05374 times 16 over square root of n, because we're multiplying the 16 over square root of n on both sides. Now what we could do is we can move that, so 16 is equal to 2.05374 times 2 times 16 over square root of n. I said 2 because if you move the negative sign to the right side, this will make it positive. So it's eventually becoming 2.05374 plus 2.05374. That is equal to 2.05374 times 2. Because if you move this to the other side, that just becomes 2.05374 plus 2.05374. That is same as just times that 2, right? So I just wrote it this way for my, I guess, complicity. Not complicity, but for my, yeah, to make it easy for me. Anyways, then if you do that, you can just divide 16 on both sides because they both have 16. And then you can move the square root of n to the other side. So that becomes square root of n is equal to 2.05374 times 2. Okay, so n value is 2.05374 times 2 squared. If you do that, 2.05374 times 2, and if you square it, this will be like 16,87139. And then since the sample size value, if the n is a sample size, you can't have a decimal number for the sample size. It has to be a whole number. So if you round up, this will just becomes 17. So the answer for the sample size is n is equal to 17. So that is it for the practice exam.